Afternoon. We continue with the chapter 9 now. So in chapter 9, what we'll be looking at is essentially systems with variable number of particles. So there are two ways of to have this variability of number of particles. So the first case is to have two different systems, system A and system B, for which particles from system A and system B can sort of flow into each other. And but the total number of total number of particles should be kept constant. So Na is the number of particles in system A, and Nb is the number of particles in system B. So this has to be kept constant. So in other words, any variation of these numbers should obey this equation, or in other words, one could rewrite this as a differential, like a derivative kind of thing. The Na over the Nb equals to -1. So this is sort of one way to do this. So there are two ways. The other way is to have some kind of like a chemical reaction. Second one, consider kind of chemical reaction. And one can have, say, atoms of C type interact with atoms of D types to form molecules of CD type, and the CD molecule could also disassociate into the respective atoms. So Nc, let me just write this. Nc will be number of C atoms, Nd is number of D atoms, and Ncd is number of CD molecules. Okay. One would require that, take for example the C atoms. C atoms can sort of interact with D, so you may lose the number of atoms for C to this reaction to form number of the same number of molecules of CD. So in other words, what one has is essentially whatever C loses out in the reaction must be appearing in this CD molecules. So in other words, this has to be kept constant. So in other words, what do we have? D and C plus D and CD has to be equal to 0. And similarly, the same thing, you can apply it to the D atoms. It has to be kept constant. There's a bit of lag. So just like before, we could write this like a derivative kind of thing. So you have D and C divided by, D and C D divided by D and C to be equals to -1. And similarly for D and C, D divided by D and D is -1. And that will tell us that D and D, D and C has to be equal to +1. So let's consider some physical examples for this. Okay, so physical examples for this are essentially like examples here are like salt in solution. Okay. So here you can have salt dissociates into Na plus ions and chlorine ions, but this can also recombine to give you the salt solution again. Okay, so that's one example. Another good example is the plasma inside the sun. For example, you have electrons interacting with the protons, for example, to form hydrogen atoms. So we will discuss this idea of plasma later on as we do some calculations. Right, so how do we actually determine what's the condition for, say, equilibrium and things like that? So when you have equilibrium, that means the entropy is going to be the maximum, okay? And one should look at, for example, let's take the first case again. First case. So one looks at the total entropy to be given by entropy of A plus entropy of B. Okay. So if there are any changes, yes, one could write this as follows. It will be ds A over dna partial as A partial and A times dna plus partial SB partial NB dnb. Now DNA and DNB are related, so one can sort of bring the factor of DNA out giving that as partial NA, and then DNB, remember we had DNB DNA equals to -1, so that would just give you minus sign in this part. Okay. So, and one can relate these things in the curly bracket with something we have essentially mentioned some time ago, which is the chemical potential. So we write this as mu A minus mu B, where mu is essentially given by this form. Lagging there, so I have to be careful. Partial S, partial N, partial N, okay, for each particle species. Right. So as I said earlier, when it achieves equilibrium, in this case chemical equilibrium, then one should have your entropy to be the maximum and there will be no further change. So in other words, the S will be equal to 0, which implies that, okay, in the case of chemical equilibrium, we require that mu A equals to mu B for chemical equilibrium. Okay, so this is for the case of the variability having the two systems A and B. What about the second case where you had a reaction? So let's try to do that. And this is a bit more complicated than the one before because you have to consider 3 different particle species here. And their entropies, which is additive, as we know that entropy is an extensive quantity. So again, we need to see the variation of this. But let's remind ourselves that in this case, we require that the decrease of, say, NC and ND by 1, see, implies an increase of NCD by 1. Okay. So, meaning we have to impose the conditions earlier that we have seen before. So let's consider the change in entropy now. And since NC, ND, and NCD will have some relationship between each other that we have mentioned before. So we bring out DNC outside, and this will be partial S, partial NC, plus partial S, partial ND. Remember, D and D would be the same as DNC, and then minus partial S, oh, I should write down also the symbol here, subscript. Okay. And if this is at a chemical equilibrium, so ds equals 0, and remember that this we can rewrite in terms of, let me just write that out first, d minus dnc on t equal times, mu c plus mu d minus mu cd. So this is will be 0, which implies, for chemical equilibrium, which implies that mu c plus mu d equals to mu cd. And one could elaborate this to more elaborate chemical reactions. Then again, you will have something like this. The general case, I'm not going to write down and read this in the book. So you have some mu i mu I equal to some mu j, where on the left hand side is essentially